Excellent. So it looks like we're live. Thank you so much, Alyssa, for that excellent talk. It was great. Now, for our next speaker, we're going to have Doug Strain from Google talking about quantum chess. Doug is the lead for the quantum computer software group at Google and manages software interfaces for quantum hardware and simulators. He's been at Google for 8 years, working on data processing for employment and jobs before joining the quantum team. He has worked at Fermilab National Laboratory and has done consulting at many large corporations. He trained in quantum computing at the University of New Mexico and got his undergraduate from Carnegie Mellon. He is also an avid chess player and works on quantum chess as a side project. So it's very fitting that he's going to be giving this talk to us today. Another note from, he wanted me to say this, and I think it's really good too. This tutorial is about quantum chess, but if you are a beginner to quantum computing or don't understand too much about quantum in general, understanding this talk will be very helpful in understanding quantum concepts, and also will be very helpful for maybe if you want to submit a project in the future and understand more, or if you want to tackle a non-technical challenge. So without further ado, Doug Strain.
Okay, yeah, thanks for the introduction. So as mentioned, this is going to be about learning quantum computation with the example of quantum chess. So we're going to have two goals in this presentation. The first is just going to be to learn some of the rules of quantum chess. It's a pretty fun game, so you can download it later on Steam, and I think there's a demo on the web. And just kind of, if that's all you get out of it, that's fine. Now you know a new fun game. But sort of our second goal here is to learn a little bit more about quantum computation with this as a motivating example. So there's a lot of ways to learn about quantum computing. The sort of typical way you see a bunch is, people explain what a qubit is, and then they jump into a lot of mathematics. So I, for one, love a good matrix multiplication, but I understand that's not for everybody. So we're going to use this as an example, and hopefully, quantum chess is going to click for you a little bit better than, some of these mathematical examples. So like any good game, we're going to have 3 levels to this presentation: easy, medium, and hard, or learning about some of the concepts of quantum, learning about the gates, and then kind of diving into some of the more advanced concepts that you have to tackle as you work on real hardware. Okay, so the first part, we're going to introduce some of the rules of quantum chess and learn about how they interact with some of the principles and ideas and concepts in quantum computing. Okay, so first let's talk about classical chess. So I'm not going to go over all the rules of classical chess, but I'll just kind of give you a flavor. So there's different pieces on the board. Each piece is on a square. And more importantly, there's kind of 2 sort of categories of moves. There's a jump move where the king can move 1 square at a time in any direction, and a knight can move sort of in an L shape. But for both of these, it doesn't matter what other kind of pieces are in the board. Like the knight can jump over pieces. That's why it kind of looks like a horse. It can jump. And then there's a second type of move called a sliding move. So this is where a piece can move in a line along one direction. For bishops, it's diagonals. For rook, it's up and down and left and right. And for queen, it's the combination. And these pieces can move as far in one direction as they want, as long as there's no pieces in the way. So if there's a piece in the way, it has to stop. So if it's a friendly piece, it can't move into that square. And if it's an enemy piece of the other side, it captures that piece, but it can't jump over the piece. It has to stop at that point. Okay, so for quantum chess, it's the same rules as classical chess. All the pieces move the same way, but there's basically one additional component, and that's called a split move. So a split move is such that a piece can move to 2 legal squares. So it has to be legal squares that they could have moved to in a classical game. And both squares have to be empty. So if you pick 2 squares, you can move to both of those squares at the same time. So in this example, in this diagram, the knight is on B1. A knight moves in an L shape, so 2 in one direction and 1 in a different one. So this knight on B1 can move to the A3 square here, and then the c3 square. So those would both be legal moves in classical chess. And in classical chess, you have to pick one of the squares and move there. You have to pick up the piece, move it there. In quantum chess, we're going to allow the move so that you can move to both of the squares at the same time. And this is called superposition. So once you do this, this knight is going to be in superposition in both squares. So what this means is if you actually measured the board, there would be a 50% chance that it would be on one square or the other. Okay, so let's talk about this a little bit more. So after you do this, you're in this new state that you can't really see in a classical chessboard, and this is called a quantum state. So once you split into these two squares, now you're in this state where you're in kind of both states, and then we call this a state vector. So you'll often see, you know, there's usually a term in front. In this case, it's 1/√2, and this is kind of a normalization factor, so that all the probabilities add up to 1. You can't have like you know, 75% chance that it's on A3 and 75% chance it's on C3, because then the probabilities don't add up to 1. So you need this special kind of factor there. And those kind of follow your state vector around if you actually do the math to do it. And then you have these two things called kets. So this is a notation that's often used in quantum computing, where you say, and you know, normally you call this square A3 and C3. Because we're quantum and we feel special, we're going to put these, you know, brackets around it to designate that this is really a quantum state, that you're sort of in, you at least have the possibility of being in superposition for multiple squares. Okay. So we're going to talk about sampling. So I mentioned that, you know, if you measure this, you have two possibilities, that the knight can be on A3 or C3. Okay, so at some points in the game, you trigger this measurement. And when you trigger the measurement, you go from this quantum state where you're 50% in both, or in this superposition where you're in both states, to either definitively in one state or the other with, you know, 50% probability. So this is done with something called measurement, where you take this quantum state and turn it into a classical state with some probability. Okay, so to kind of illustrate this, there's sort of 3 steps in how this happens. So there's first this quantum state where you're in both states at the same time. Then you go to a probabilistic state where you're in one or the other, but you might not know which one. And then you're going to do this thing called sampling. So since we don't really know which one you are, to kind of get good statistics and figure out, you know, if it's a 50-50 chance or a 75-25 chance, you're going to repeat this measurement over and over. So you're going to do the same sequence of like quantum operations and then measure it at the end, say 1,000 times, and get some sort of probability distribution out. So another analogy that you can think of is flipping a coin. So if you flip a coin, that you can kind of go through these sort of same states, right? So when you flip a coin and it's spinning in the air, and you ask, is it heads or tails? While it's spinning in the air, this doesn't really have any meaning, right? You have this state that's kind of halfway in between. It's spinning. It's both heads and tails, right? Like it's not in either one. And that's the same case with this quantum state, where you're in this special state that's neither on one square or the other. It's kind of this superposition. It's in both squares, right? It doesn't make sense to say which square it's in. It's in this other thing that's in both. And then so if you go back to this coin analogy, eventually the coin falls down, you catch it and you put it on your wrist or whatever, but it's covered up. Now, at this point, the coin is in heads or tails, and you say, you know, is it heads or tails, if like this was at the beginning of a sports game or something. So at this point, the coin definitely is in heads or it's in tails. You just don't know because it's covered up. So this is sort of your second point of like a distribution where you've kind of taken this quantum state and you've turned it into a classical state with some sort of probability distribution. So you don't know if it's heads or tails, or if the knight is on A3 or C3, but it's definitely on one of them, and it's going to be on one or the other with 50% probability. And then this third state is, if you flip coins over and over, eventually you can figure out whether your coin is fair or not, whether it's balanced by seeing how many heads or how many tails. And that's the same thing with this quantum position, that if you repeated this move sequence a whole bunch of times, you could eventually get statistics about whether the knight is, 50% on both. So this process is called sampling, where you take a quantum state, you turn it into a classical state, and then you repeat this over and over to kind of build up some knowledge of what actually happened. Okay, so the reason I talk about this is because this is going to come up when you use simulators. So the next talk is about circ and simulators, and I didn't listen to the quiz kit one, but they probably also mentioned simulators there too. And in particular in circ, there's these sort of two implementations of a simulator, or two interfaces rather, where you can simulate and you can run. And the reason you have these two is because you're asking different questions. So in a simulator, you have access to this quantum state because you're kind of keeping track of like what the state of the system is. And the same thing when you run this when you play quantum chess, you can see the statistics of all the pieces on the board and what their states are and whether they're entangled or not. And this is because we're simulating it. It's not a real like quantum system. We're just pretending it is, right? So this is, you have access to the state vector. In the real world and in real quantum devices, we don't have access to this quantum state. It's this thing that's kind of intermediate, where it's in a quantum state, but at the end, we're macroscopic creatures, right? We're in the classical world. We have to get some information out of this quantum state. So when we sample, we have to measure and turn this quantum state into a classical state through sampling, right? So every time you talk about real hardware, there's no really observation or way to access the quantum state directly. We have to do it through this process of sampling. And that's why we have to do this repeated thing over and over again, is because we need to do that to find enough information to figure out what the quantum state really was. So there's some examples here on the slide. So for a photonic devices, we either see, a photon going to one detector or the other. We don't see, it's got to show up at one or the other. For supercomputing qubits, what Google uses, you kind of ping the device and either get like a 0 or 1 when it comes back. And with quantum chess, the piece is always eventually going to be on one square or another once you measure it. So people have used all sorts of metaphors for this. Our metaphor is going to be chessboard. We prefer not to use, metaphors of dead cats, but that's also one that shows up all the time as well. Okay, so let's do another example. So I talked at the beginning that some of the pieces, like a bishop, can slide along the board in one direction. So what happens when you slide along the board and there's a piece in superposition that's in the way? So in this position, the knight has split to these two squares. So we've got a knight in 50% probability of being in B2 and 50% in A3. And I'll remind you that I'm kind of using that as a shorthand, that really we're in this quantum state where it's superposition between B2 and A3. So this bishop is going to try to move through this knight. So the knight is there, but it's also not there at the same time. So what would even happen here, right? So this move is only going to be legal if the knight's not there. So the path is clear, right? So there's two examples here. So in the first one, if the knight was on B2, then this move is illegal. And in quantum chess, if you try to move something and it's illegal, nothing happens, and basically your turn is skipped. So that's a little bit different than classical chess, where it's just not allowed. In this case, your kind of turn is skipped. If the knight is on a3, then this was legal, and the bishop actually moves to c3. So if we try to do this in quantum chess, the state we're going to get in is this, where we have this bishop in 50% superposition, where it's in superposition between c3 and a3, and the knight is in superposition between b2 and a3. Okay, so that's interesting. Let's do some basic like probability math. So there's a 50% chance of observing the bishop on either a1 or c3, 50-50, makes sense, right? And there's a 50% probability of the knight being on b2 or a3, right? Okay, so hopefully in grade school you've learned that you can multiply probabilities together to get the probability of both of them happening. So we can multiply this together and get 25% chance of seeing the bishop on c3 and at the same time seeing the knight on a3, right? Okay. So if you've been careful in listening to me, you'll notice this is completely wrong. So these two, this kind of trick of multiplying probabilities only works if the events are independent. And these events are not independent, right? The bishop can only move if the path is clear. So you would often say in probability terms that these two events are correlated, right? So the two are related in some way. The quantum term for this is actually entanglement. So, with the knight having two possibilities and the bishop having two possibilities, if you consider the scope of the universe of possibilities, or the state space as it's sometimes called, there's kind of four possibilities. However, really only two of them are legal in this position, not all four, right? So it's a superposition of only two states. So there's the knight on a3 and the bishop on c3, and the bishop on a1 and the knight on b2. So the other two possibilities with the knight on a3 and the bishop on a1 are that's not a legal possibility, because the bishop, in that case, the bishop would have been able to move. So this is called entanglement, because now these two pieces are entangled. Their positions depend on each other. So in this case, if you go back to this ket notation, you see this normalization factor again, and then you see there's actually only two possibilities, and we put these kind of things together, right? So there's the possibilities are a3 and c3 and a1 and b2. The other two states, a3, b2, and a1, c3, are just not in this state. So if we were to kind of sample this and repeat it a whole bunch of times and measure it, we'd get about 50, half the time it would be in one of these and half the time it would be in the others. And if we got those other two states, it would be some sort of error or noise in our quantum chess things, which wouldn't happen in a simulator, of course. Okay, so I'm just going to take a brief aside here and say, if we kind of relabel these terms, and I take those squares and, substitute out some zeros and ones, we can change this into this normalization pattern and 0, 0, 1, 1. So if we, instead of squares and chess pieces, we say these are two qubits. Now these two qubits are entangled in this particular example, and I've accidentally taught you something called the Bell state, where this is one of the simplest examples of two entangled qubits, where these two qubits depend on each other. If you measure one qubit, it's going to be the same as the other qubit. You don't know whether they're both zeros or both ones, but they have to be one or the other. And this state and entanglement in general is very important for lots of quantum algorithms out there. The most, this is used for quantum teleportation, for instance, and basically every other important algorithm uses entanglement in some sort of fashion in order to get extra oomph out of and extra computation out of your processing. Okay, so the next thing I'm going to mention is you'll often hear something called unitary operations. So unitary has a very specific meaning in matrix multiplication. The technical definition is that if you kind of flip the matrix on the diagonal, so you take the upper right-hand corner and make it the lower left and vice versa, and you also flip the sign of any imaginary numbers that are in there, and then times it by itself, it just cancels itself out. So that's kind of a complicated like math term. But the idea here is that, you know, if we do an operation on a quantum state, the probabilities still have to add up to 1. We can't have like do an operation and then suddenly have like probabilities not add up to 1, because that wouldn't make any sense anymore. Like you wouldn't have a system that makes sense if like they just have to add up to 1. You know, it's just reality, right? So in order to kind of guarantee it, we have to put this condition on there. This also has a lot of other effects. So one thing is that because each of these operations has this like fact that it has an inverse, that means it's reversible. So anything that you do in the quantum world, you can actually go and undo. So you can find some way to go to kind of do all your operations and then undo them back to your original state. So if you had a noiseless quantum computer or a simulator, that for anything you do, you can undo it. Okay, so this also has another interesting thing in that because you can undo it, you can't ever lose information. You can't go to a state where you can't get something back. If you had information in your original like state, whatever definition information is, you have to be able to get this back out. Okay, so let's do 2 examples here. The first one is assignment. So assignment is something you learn in every classical programming class. It's basically like one of the first things you have to learn because you need it for like everything, right? So if you say, you know, A equals 4, that is not reversible because at the end of this, A is going to be equal to 4. And if I ask you what was A before you did this, you have no idea. It could have been 1, it could have been 0. You don't know what A was before you assigned it to 4. So this is not reversible, right? You can't undo an assignment because whatever was in there is now lost. There's no way to kind of get it back. Another example is if I tell you this operation is guaranteed to double your chance of winning. For some, you know, definition of winning at like blackjack or the lottery or something. So this is not a unitary operation because if you had a 51% chance of winning before this, and then you did this, you would now have, if you doubled that, you'd now have 102% chance of winning, which doesn't even make any sense, right? So this is not unitary either, right? So these are kind of 2 like sort of silly, but simple examples of explaining, you know, that these things have to, these operations that you do to your quantum states have to obey these certain principles. Okay, so reversible chess moves. Let's talk about that. So looks like I have a diagram missing. Oh, okay, here we go. So a normal chess move, you can just kind of like if you take a piece and move it to a different square, that's reversible, right? So you could take it from that square and move it back, right? So if I take the knight and move it from, you know, A3 to B1, in order to undo that, I just have to pick it up and move it back to the original square, right? Okay, fine, great. So split moves are a little bit more complicated. So because they're quantum operations, they have to be reversible. So we have to also allow the reverse of this quantum move to happen. So this is called a merge move. So this is an additional type of move that is allowed by quantum chess is if you have two pieces in superposition, you can move them together in the same square. So if I have a knight that's in superposition on A3 and C3, I can combine them together in this thing called a merge move. And now the knight is going to be in a pure state, or a 100% probability of happening on B1. So this kind of undoes the split move. So you can do a split move, split it into two different squares, and then combine it again. So it's all on one square. Right, okay. So a question, if you think about it. So are there any chess moves in normal chess that are not reversible? So is there something you can do on a physical chessboard that you can't undo, or at least not undo, you know, trivially? Okay, so I'll give you a second to think about that. And the answer is yes, there is a move that is not reversible, and that's capturing. So if you capture a piece, so if I, you know, take a piece of the other side, so I take my knight and capture, say, an enemy pawn, right? That pawn disappears from the chessboard, right? So at least kind of at first pass, this is not, there's not like a good way to undo that, right? So if I say, if I give you just the chessboard, I don't tell you like what happened, I just give you the chessboard and I say, okay, now undo this knight move. Now you can certainly take the knight and move it back to its original square, but now you don't know the square that it just came from. Did it capture something, or was that empty? There's some sort of information lost here that now you don't know what was on that square before the knight moved there, right? It could have been empty, or it could have been a capture, and now we don't know. So that's a problem, because that means our quantum chess is not actually a quantum operation anymore, because it's not reversible. And if you think about this a little bit more, this is a bigger problem, because, you know, aside from quantum chess, if you can't do anything irreversible using quantum operations, that's really going to limit the scope of what you could possibly do with a quantum computer, right? So, I mean, the fact that just assignment, which is like the most basic classical thing, you cannot do on a quantum computer, that's really going to cause you some problems, right? Because that means like every program you've ever written probably is not translatable to a quantum computer. So that's a problem. And, you know, it's going to be something we have to solve if we want to make quantum computers at all useful for anything, right? Okay, so the way we do it is something called an Ancilla qubit. So an Ancilla qubit is basically just extra qubits that are around, or extra, in this case, our qubits are squares. So we're going to have extra squares that are around, but are not actually on the chessboard, right? So you can think about this in like normal chess terms, like what you would do if you actually captured a piece. So when you capture a piece on a chessboard, you take that piece and put it to the side of the board, right? Okay, so that's what we're going to do here too, is we're going to take this and we're going to set it in a specific place on the side of the board, so that if we ever have to like undo and go back to what we were before, we're going to do the same thing we do in like real life, right? We move the knight back, and then we take that piece that's on the side of the board and put it back on the board, right? So by using these extra squares that are sort of off to the side of the chessboard, now we can represent this operation by saying, okay, now with this extra qubit, it is reversible, because all we did was kind of take the piece and put it on a different square. We didn't actually get rid of it or destroy it or anything. It's just, you know, sitting in a, you know, standby spot, right? Where it's just sitting on the side of the board. Okay. The next thing I'm going to talk about is measurement. So I've kind of alluded to this a few times, that at some point in the game, you're going to want to measure and figure out where these pieces in superposition are. So the rules on this are a little bit complicated, but I'm going to simplify them for this presentation and say essentially the main point at where you would measure something is if you try to capture with a piece that's in superposition. So for instance, if you have this rook here and you're trying to capture the knight. So the rook is in a superposition. If measured, it would be 50% there and 50% not there. It's in this kind of mixed state here. And when we capture it, though, now we have to know what to do with this knight. Like, is the knight still there or not? So this move in the rules of quantum chess triggers a measurement of the rook, because we at this point we kind of have to know whether the rook's there or not. So we know whether to do a capture or whether to just move it. So there's two possibilities here. Either the rook is there or it's not there. If the rook is not there, it's illegal. So the rook just kind of disappears. We know it's not there anymore. If it is a legal move, then the rook can capture the knight. Okay. So I'm going to do a big exercise here, and we'll kind of combine all these concepts together and see if it now makes sense. Okay. So here's the starting position. We're going to run through a few different moves and then see if you can figure out like what the state of the system is. We're going to take these two bishops. We're going to do a split move where each of these bishops move to two different squares. One of them is going to be in the path of this queen, and one of them is going to be off the path. But now there's going to be two different bishops that are both in this state. So then we're going to take this queen and try to slide through both of these bishops in superposition. And then lastly, we're going to force a measurement by taking this queen and trying to capture this rook. So by trying to capture the rook, now we have to know, does this queen exist on this square or not? So it's going to measure the queen and something's going to happen. Either we're going to have one possibility or the other possibility. Either it's there or it's not there. So first of all, before we do the capture, you can see now that the queen is in this superposition, but it's not an equal superposition. So each of these exercises we've done so far, it's been 50-50. But now it's not 50-50, right? Because this queen most likely couldn't move because probably one of the bishops was here or both. But there is a possibility that both of the bishops were here, right? So there is some probability here, and you can see this by these lines not being, you know, halfway. So that this is, you know, there's less of a probability that the queen is here than here. And that's how we kind of visually note it in quantum chess. So when we measure this, what's going to happen? Okay, so we definitely know there's two possibilities. Either the queen is not there or the queen is there. So we can kind of go through these two possibilities. So one, let's do the one where the queen was there. So if the queen was there, then we know the path was clear. So these two bishops were not there. So they must have been on the squares that were off the path. So the bishops we know are on A3 and B4. We can kind of figure that out logically. And the queen was there, so it's a legal move, so it can capture this rook. So we know if we measure the queen there, this is now in this kind of classical pure state where everything is defined. Like we know where all the pieces are at this point because the queen was on D4, it moves, it captures the rook, and we know for sure the bishops were off the path. The more complicated possibility is if the queen wasn't there. So if we measure that queen and it was not on that square, well, the first thing we know is there's only two possibilities. The either queen moved or it didn't move. So if we measure that square and it's empty, we know the queen is over here in A1, right? Okay, cool. And we know it. We also know because it's way over here, we can't capture the rook. This whole thing was illegal because the queen, you tried to move a piece that wasn't even there. So that's illegal. Your turn is skipped, right? So the rook is still there. Cool. What about these bishops? So the bishops now, you know that because the queen is on its original square, at least one of the bishops was there blocking the path, right? And it's possible both bishops were there too. So there's kind of this three out of the four possibilities are here, right? Either the first bishop is blocking, the second bishop is blocking, or they're both blocking, right? So now you can see actually by measuring the queen, you've changed the probabilities of these bishops occurring on these squares. Even though you kind of never touched the bishops, because the queen was entangled with the bishop and you measured the queen, you've actually modified the probability and the distributions of what can happen with these bishops. So I would say this is an example of entanglement and seeing sort of this action at a distance, right? Where by modifying a chess piece or a qubit, you can also affect any other qubits or chess pieces that are entangled with it. So you kind of visually see this like interaction between the other pieces. Okay, right. So this is a good chance to ask any questions. So we've kind of gone through our first level, the easy level, to talk about kind of quantum concepts, and next we're going to talk about quantum gates. So maybe we could take any questions if there are any at this point.
Yes, someone actually just asked about the example you just did. He's saying in this example, would the bishops now be entangled if you could go back to?
Yeah. So right. Yeah. So the bishops in this case are entangled. So in this case now, there's four, like in the universe of probability, there's sort of four possibilities that could happen. You know, each of the bishops could be on one of two squares. So there, in total, there's four possibilities, but one of them is not possible, right? The possibility of the bishops being on A3 and B4 is impossible, right? So you've got 3 out of these 4 probabilities. So actually both of these bishops are now entangled because their positions actually depend on each other, right? So you can think about this as if you, for instance, measured this bishop and you found out that it was on A3, right? Now you know for sure the fact of this other bishop is not, it's not on B4 because they can't both be there, right? So logically it has to be in this other square, C3, right? So you now know that by measuring the first bishop, you get some information about the second bishop, which means they're entangled, they're correlated, right? Their probabilities are correlated. So now you know they're not independent and they are, entangled. Okay. Any other questions?
Someone actually just asked, I think this is actually pretty interesting. Wow, I just realized this intuition expands to the Monty Hall problem and the concept of variable change. Is that a fair deduction, or is my understanding flawed somewhere?
Yeah, so I'd have to think about this a little bit in terms of Monty Hall. But I think that it would be fair to say that the Monty Hall problem is an example of classical correlation, where outcomes are correlated rather than, quantum. It's the state at which the door behind which the prize is in the Monty Hall problem is defined. It's a classical probability rather than a quantum state where it's in some sort of superposition. But by seeing what's behind one of the doors, you learn some information that you didn't know before. So it is kind of similar, but it's the classical analogy of this. Okay, cool. So let's go on to the medium level, level 2. We're going to talk about we've kind of talked about chess pieces and things. Now I'm going to show you how does this actually work under the hood. And we're going to learn a little bit about quantum gates in the process. Okay, so quantum chess is backed by quantum computing circuits. If we actually want to play a game of quantum chess under the hood, it's going to be running these quantum circuits in some way or fashion and simulating the results in order to kind of generate these like distributions and the visual results of seeing whether things are 50-50. The implementation is that each square on this board is a qubit. And if there is a piece on there, it's in the one state. So it's going to be, you know, true or one. Empty squares are going to be 0 or a 0 state. And each move that we do is going to be a quantum operation. So it's going to change the state by some way so that it's going to kind of move the pieces around, okay? Or a set of quantum operations where you do multiple things. Okay, so what quantum operations are we going to use? So let's first talk about something called the swap gate. So the swap gate is something hopefully anyone who's taken a programming class can understand swapping something, right? You take one variable and you move it to another, and you take that variable and move it to the original space. Okay, so here's two examples of how to do that. A simple Python function that just kind of swaps the two and returns them as a tuple. Or you can do this goofy assignment thing using a temporary variable and swap the two at the end by using kind of the temporary variable so you don't, you know, clobber the first one. Okay, so a quantum swap gate is going to do a very similar thing, but it's going to swap 2 qubits, the values of 2 qubits. Okay, so for a classical swap, if you call this function and the two variables are the same. So let's assume that you're calling this swap function. You've written something in, you know, Python or something, but the two variables are either going to be 0 or 1. You know, they're, you know, Boolean values or 0 and 1 integer or something like that. So if you call it with 1 and 1, it's not actually going to do anything. It'll swap those two values, but the values are going to be the same because they're the same, right? So same thing if you pass it 2 zeros. You'll still get out 2 zeros at the end. So the interesting thing is when you pass it with a 0 and a 1 or a 1 and a 0, then it's going to swap these two classical values. So the same thing is true with this quantum state. So you can pass it this thing that's 2 qubits. So there's either, you know, each of the first qubit can either be 0 or 1, and the second qubit can either be 0 and 1. So there's 4 possibilities, right? In the 1-1 state and the 0-0 state, those 2 qubits are the same, so it doesn't do anything. In the swap case, you swap these 2 qubits. So the 1-0 case becomes 0-1, and the 0-1 becomes the 1-0. So this is essentially the same thing as a classical swap, right? The tricky part is that quantum gates can act on things in superposition, right? So we've already seen with this bishop moving through the knight and the queen moving through the double bishop thing, is that, you know, interesting stuff happens when you start acting these things on things that are already in superpositions. Weird stuff starts happening, right? So in this case, you could have something that's any combination of these 4 different values. And it's going to swap the middle too. So the whatever component is 1-0, you know, if it's, you know, a quarter or a half, that goes to the 0-1, and the 1-0 or the 0-1 goes to the 1-0. So these two are going to basically swap. And it's going to change whatever component was in the 1-1 and the 0-0. It's just going to leave those alone. Okay, cool. So that kind of makes sense. It's very similar to a classical thing. So let's talk about an ISWAP. So an ISWAP is distinctly quantum. So we're going to take this swap gate and we're going to add this value of I onto those 2 in the middle. So it's going to take these 2 middle states, it's going to swap them, and then it's going to throw this imaginary number I in there. This thing is called a conditional phase. Okay, cool, interesting. So this is the first time we've talked about imaginary numbers. What is that, right? So one of the powers. And sometimes the frustration is that, we're not actually working directly with probabilities, we're working with these amplitudes. We've talked about that, where there's a difference between superposition, being in this quantum state, and being in a probability distribution after we measure, right? And this difference is the difference between probabilities and amplitudes. And these amplitudes can have complex values. So you should all know from high school algebra, or that complex value is a plus bi, right? And these amplitudes all have to, when squared, have to add up to 1, because your probabilities have to add up to 1. So one interesting thing is that these amplitudes can have different values that have the same probability. So if you time something by I, it makes it imaginary, but it's not actually changing the probability that you see it. So this turns out to give us a lot of computing power, because we have a lot more space to play with in terms of modifying these amplitudes. But it also gives us a lot of difficulty because we can't directly measure this phase. So we have to do a lot of goofy stuff, like kind of changing the state in order to see what the amplitude is. And the other bonus is too, unlike probabilities, amplitudes could have negative values. So because they can have negative values and we square them to get the probability, then these things can cancel out. So that's really cool, because we can't cancel out probabilities classically, but we can cancel out amplitudes, which gives us interference and gives us a lot of power. If we can destructively interfere states that we don't want, and constructively interfere states that we do want, we can kind of amplify states. So quantum chess uses this imaginary number, this ISWAP, to kind of give you this feel of phase, and to kind of introduce this concept to help you understand it a little bit more. Okay, the next gate I'm going to talk about is called the square root of ISWAP. So hopefully you know what a square root is. So if you, for instance, the square root of 2, if you times square root of 2 by square root of 2, you get 2, right? So the same thing works with the square root of ISWAP, is if you perform it twice, so square root of ISWAP times square root of ISWAP, you get an ISWAP. So you can think of this as kind of musical chairs, where you're trying to swap chairs with someone, but you're only halfway there. Like you haven't quite made it to the next chair before the music stops. And the key thing of this is that it can create superposition states. So we've kind of shown this diagram where quantum ISWAP, you're swapping these two and you're adding I. For the square root of ISWAP, now it's starting to get a little bit more complicated, but it shouldn't be too bad to understand, because half of this thing is going to be the original state. So 1, 0, 1, 0, you can see in the first line, and this 0, 1 stays 0, 1 half the time. And the other half, it's this I of the swap state. So it's kind of putting this in this superposition where half of it is not swapped and the other half is. And if you run this twice, do all the math, you wind up that this kind of swaps the other half, and you get this ISWAP. Okay, so let's talk about some example quantum chess moves. So a jump is just an ISWAP. So if you move one piece to a different square, you're doing an ISWAP. So if the piece was on the first square, it's going to be 1, and then the other square is empty, so that's 0. So it's changing 1, 0 to 0, 1. So when you do this swap, now instead of the 1 being in the source square, it's going to be in the target square. So you've essentially moved a 1 from one square to another, just moving a chess piece, right? No problem. The split move is a little bit more complicated. We're going to combine these two gates together. So we're going to do a square root of ISWAP. So this is going to swap half of it with the first square. So now we're in this state where we're half swapped and half not swapped. So half of the amplitude or the probability is going to be in this first square, and the other half is going to be in the original square. And then we're going to move the rest of it using an ISWAP from the source square to the second target square. So at the end of this, half of the sort of amplitude is going to be in this first target square, and the other half is going to be in the second target square. And a cool thing is that since quantum moves are reversible, we easily know from this what the merge move is. It's just going to be kind of the inverse of this, so like doing it backwards. So we swap it back and then do sort of the inverse square root of ISWAP to swap it back here. So it's kind of like the mirror image of this move is just going to be the merge move. Okay. I think this is the last gate I talk about. It's called the control gate. So that we talked about this move here, where we want to do something where we want to move this bishop only if the path is clear. So if the path is clear, we want to move the piece. So we want to perform this ISWAP gate in order to move it from A1 to C3. So we do this by doing a controlled ISWAP gate. So the control is this knight. So this knight kind of controls whether the ISWAP happens or not. This is kind of the diagram of that. So there's also a little bit simpler example of what's called a controlled NOT gate. So flipping a bit based on a control. But basically, if this thing is, if your piece is, if everything in the path is clear, then you want to perform this ISWAP. And if it's not clear, then you do not, then you leave the state alone. And that's called a controlled gate. Okay, cool. So the last part I'm just going to kind of brush through. We're starting to run out of time, but I want to kind of give you a little bit of a survey of what more you can talk about with quantum chess if you really want to get into it. And a lot of this has to do with taking quantum chess and putting it onto hardware. So a lot of this stuff is kind of in simulator mode, where you're taking states and looking at them and figuring out things in like a simulator where you have the full state. If you want to do it in hardware, it's a little bit more complicated. And here are some of the reasons why. So one reason is that as you kind of stack moves on, we've been kind of talking about moves in isolation, but if you talk about a whole game, in order to kind of think about a whole game, you have to do a whole bunch of moves. So you start with your starting position at the very beginning of the move and start adding these moves onto the qubits one at a time, right? To make this whole game. So you start with the, like if you're on move 10, say, you start with the starting position, then you do 10 quantum operations and you've gotten to the current position on the board, right? Okay, well, that's no big deal. I mean, we can always do more quantum operations. But the problem is, what if we need to measure something in the middle? So if we needed to, do that big example with the queen, and we measured and we found the queen wasn't there, and then we keep moving pieces, how do we do this now, right? There's this big measurement in the middle of this circuit, right? So let's say we want to do another move. So we start at the beginning, we start with the starting position, we run through all the moves, we measure, we get the wrong result and then do the next move. Wait, we got the wrong result. Uh-oh, what do we do now, right? Like if in the original game we measured 0, but the second time we run it, we measure a 1, what do we do now, right? We're not in the same place we were in the game. So this isn't a problem in simulation because we can just keep track of what this quantum state is and just kind of slowly continue. But if you wanted to do this on hardware, you can't keep this quantum state on like a quantum hardware while someone's, slowly pondering their next quantum state. These states only last like nanoseconds, right? So you don't know what to do, right? So one of the ways you do this is post-selection, where you run this a bunch of times, you get a bunch of samples like we talked about, and you only keep the ones that match what happened in the original game. So this is called post-selection. So that's interesting. You have to deal with that. Another thing is gate decomposition. So different hardware handles different gates. And especially when you're talking about more complicated gates. So a controlled ISWAP is a 3-qubit gate. Google's device, and most devices for that matter, only handle 2-qubit gates, and only certain kinds of 2-qubit gates. So you have to take what, like, these logical operations of like controlled ISWAP or control Toffoli gate. This is an example of a Toffoli gate, which is a control knot. And turn them into 2-qubit operations, and this blows up the circuit. So you can see this one 3-qubit operation turns into, like, what is this, 15 or something different operations. So kind of the efficiency of how you do this and how you kind of compile your logical gates into the physical gates really makes a lot of difference whether you can run your circuit or not, because it might be too big. The other thing is noise. Noise happens in hardware. So none of these quantum processors that exist now work perfectly. Your simulator might work perfectly, but real quantum hardware is going to give you all sorts of things. I told you, 2 out of these 4 states are like legal, right? If you ran them in a simulator, but if you ran them on hardware, you'd get all 4 states. Like, ideally, if it's good hardware, most of the probability and most of the samples would be in the 2 out of 4 states that you expect. But there's going to be these 2, noise and errors that pop up all over the place. You might move a piece on the board and suddenly you have 2 pieces, right? Like, or that piece just disappears, right? When you measure it, you get 2 zeros, even though there should be a piece there. Like, what do you do? How do you deal with this, right? And kind of thinking about how to mitigate some of these noise and errors is one of the big challenges of quantum computation, at least in the next few years, for sure. Okay, yeah, so I talked a little bit about error mitigation, and just kind of to send you on your way, you can play chess. If you just want to play the chess, you can download Quantum Chess on Steam. There's also, you can find it, there's a web page if you just search for Quantum Chess too. On our quantumai.google, there's a long page about quantum chess and exploring some of these more advanced concepts. If you want to kind of dig into the details, you can definitely do that. There's also a full implementation on quantum chess in our research repository. This is research on Circ. You're going to learn about Circ in the next presentation, so I should probably finish up so they can start talking pretty soon. But Recirc is research on Circ, and one of our research implementations is quantum chess, so you can see, how we wrote it in Circ. And hopefully this helps you understand some of the concepts behind, quantum computation in general. Okay. So that's all the slides I have. Were there any other further questions?
Somebody actually just had a nice question in the chat, considering the amount of qubits it would take to run quantum chess on real hardware. So basically, Elam said, so a real game of quantum chess, not simulated, would require about 100 qubits.
Yeah, so if you think about it, there's 64 squares on a chessboard, so you would need 64 qubits, and you'd need a number of ancilla and extra qubits to kind of handle captured pieces, as well as, extra, every once in a while you kind of need an extra qubit for various reasons, for like path qubits and stuff. So it would require about 100 qubits in sort of the naive case. In practice, you can get this down a lot because you really only have to deal with squares that are in superposition. So any piece that is in, a classical state, you don't need to keep track of with a qubit. So in practice, you probably only need about 10 or 20 qubits for most positions if you can optimize it. But yeah, in the general case or in really complicated positions, you could need up to somewhere around 100 qubits for sure.
Excellent. 2 more questions and then we'll have to close the stream and go to the next one. But someone just asked, what are the challenges in physical implementation of 3 or more qubit gates?
Right. So, I mean, the problem is connectivity. So generally these qubits are on a grid. so they only connect with adjacent qubits or in some sort of lattice. So generally you only can do like nearest neighbor gates, which is why you need 2 qubit gates, and generally why you have to decompose 3 qubit gates into 2 qubit gates.
Excellent. And then to end off, I think this was a pretty fun question that was asked earlier, but someone asked, which classical chess world champion style do you think would be most successful in a game of quantum chess? And what is your dream quantum chess match?
Oh man. Yeah, I mean, I think someone who's very experimental and fun would be a good player to try these things out. I'd love to see Hikaru Nakamura play this. He's a really fun player, but you know, seeing any strong players would be really a fun and enjoyable experiment to see if they come up with new strategies for this variant. Would be really cool.
Excellent. Well, that's all the time we have for today. Thank you so much, Doug, for your quantum chess presentation. I see that there's some more questions in the chat. If you have any excess questions, you can go into the Discord and ask them there. And our excellent mentors from Google will answer them for you. Also, this will be recorded for all of those who are viewing. So you can just go to twitch.tv/Quantum Coalition and you can see all recorded workshops. Yeah, so now, honestly, we'll take maybe a 5-minute break, get the next workshop people set up, and then get Bala into Newshare to talk about Cirque. Thank you so much, Doug. See you guys in 5.
Okay, thank you. It was really fun.
Awesome.